Morning, everybody. I hope you've all gone ahead and tried this this tutorial. So let's just go through it. Residue curve maps are given overleaf for the ternary system: water, ethanol, benzene. These residue curves are plotted by using Aspen Plus using the Wilson thermodynamic method for 101 kPa and 1000 kPa. That's 10 bars of pressure. Note that ethanol and water form an azeotrope, and benzene and ethanol also form an azeotrope. Water is the least volatile of these compounds. So the first thing to do is to indicate the direction of the residue curves on both residue curve maps. So they give the mixture's composition. Oh wait, let me get. Oh, I can't use a pointer on this. I can use a pointer here. Yes, look at that. Okay. So we can assume that the first distillation column is operated at 101 kPa and produces pure water. So that's a nice clue already, and that is not something that you can assume that you'll be getting in an exam. Label bottom product A, distillate product B, and use alphabetic characters to show, right, and show the tie lines with the alphabetic characters that match the numbers used on our diagram. On the flow diagram, show the recycle stream, but do not show how that will affect the composition of the stream. Show only tie lines as if there were no recycle. Okay, so let me get the memo. Oops, I must go up here first. Let me get the memo that I prepared. That one. And share now. Now I wonder if we can enlarge this. I think it is possible to enlarge it somewhere. Great. So the first thing is to add arrows onto the residue curves. So let me get a pencil and make that a green pencil. Okay, the first thing you need to watch out for is where are the distillation boundaries. Now, that one obviously has been, that azeotrope, say in the question, there's an ethanol benzene azeotrope. And obviously that is lying at 55% benzene. Now, I've shown ethanol in text up there, and this is what I'd suggest you do every time you get a problem like this. That you have a look, mole fraction ethanol, and you see which side of this axis does the ethanol, where is the ethanol equal to 1? And it's up at the top there. So that one you can label as ethanol. Then you can have a look at the water, and the water is 1 on this side. So therefore you can use text. Let's see if I can put in text and put in water. I'll just put in a W there. And I'm just going to, at the same time, put in a benzene on the next one, and that will be a B for benzene. Okay, so now we've got at the bottom here water and benzene, and this one is another benzene over here, B, and here is a water. Okay, so it should be clear how to see just from these things that at this bottom axis on the right is 1, and the axis is labeled water, so water lies at the bottom over there, and that occurs on both of these things. Right. So here is an azeotrope, and now you'll see if we follow residue curves down here, you see it curves to the right. All of them are curving to the right, so there's no azeotrope down on the bottom thing. So right down this axis, across here, right down to yes, sure. Somebody want to say something?
So I think they were trying to say pointer.
Oh, I've got a pointer on my screen. I mean, I've got a hand on my screen. Thank you. That's better. Now I've got two hands. My pointer and this descriptor. Okay, sure. Right. So we'll start at this azeotrope over here. And if we take just one of the residue curves here, we can see it points to the right. All of these are pointing to the right. That means that we could assume that if we go down the axis, down to B, we could have arrows that are, the residue curve is moving in this direction, and it's moving along this axis in this direction until it gets to W. If we look at the top here, it's not very clear that this residue curve is actually going towards ethanol. But if you go to the 1000 kPa graph, you can see that the residue curve certainly goes upwards towards ethanol. So you can assume that there is an azeotrope that occurs between, excuse me, must be COVID. Right, so we're going from 0.9, and that is an azeotrope between ethanol and water. We know there is an azeotrope at 101. We usually assume that azeotrope is a little bit higher than 90%. But we know then that there's a distillation boundary that runs over here. And so I've marked that distillation boundary in blue. If you go on this side of that blue boundary, you will be going back towards water. So all of within this distillation boundary, which is the whole of the ternary diagram, right until including water. That is, so most of this diagram is one distillation boundary, and there's another distillation boundary up here, which includes pure ethanol. So we'll need to get into that distillation boundary in order to make pure ethanol. Right, let's plot where the feed is. So the feed was 30% water. So here's the water axis, and 30% water is at that point. And it must run parallel. It must run parallel with where the water is. So it cannot be this one, because this one is getting further and further away from water as it moves across that way. And the only other one from 0.3 is this way, and that's equidistant from the water point as you move along. So that is one of the lines. It also said 20% ethanol. Ethanol is over here. We go down to 0.2, and we don't want to look at this line because that moves further and further away from ethanol, whereas this dotted line is always equidistant from ethanol. And there we've already got our point, and we can check that by looking at the benzene, which was 50%. So there's benzene. All of these lines that are equidistant from the benzene represent benzene, and this is the scale. So we go up to 0.5, and we know we must go equidistant from benzene, and yes, it does in fact land up at exactly that spot. So that is our feed. Let me go back to text. And we put in text over there, that's F. Right. Now I'm going to draw a line. Because if we want to know what are the possible compositions of distillate and bottoms product, we need to draw a residue curve that actually goes through the feed point. So I'm going to try drawing a residue curve now with this strange looking like that. And then it runs all along the axis over there. Isn't that a beautiful smooth curve? And now we must color in what is the possible distillates. Thank you, Yakalui. They call it artistic. Okay, so there we go. We start coloring in. Question in the chat, right? I usually don't have chat on because I'm sharing files. On the left, you can zoom in yourself. Yep. Thank you. There's a question. Explain again how you spotted the azeotrope between water and ethanol. Yep, sure. I'm going to get to my pointer again. Water and ethanol. All right. You can't see it on this 101 curve, except over here. You can see that the curve it's got a certain slope over here at this point, and it is tending towards ethanol as it's getting closer to this point. But of course, that's difficult to tell really where the azeotrope is. Let's go across to this one, 1000 kPa. It's not shown on this thing, but here you can see something that is moving in this direction towards ethanol, and on the other side of this blue line, it's moving in the opposite direction. So that tells you there's an azeotrope at 1000 kPa, and you can start wondering, is there going to be an azeotrope? Would there be an azeotrope over here? And so you need to look at these sort of clues, like this, how the slope of this line is tending towards ethanol, but it makes a very sharp curve at this point going towards ethanol. So yes, it's difficult, but I'm expecting you to see these clues. So to illustrate that point, let's just have a look down here. You can see this is definitely curving towards water at this bottom point. Now we go over to this one, and you can see, no, you can't see on this one, but over there, just the tiniest movement to the left. That curve has got a slight curve, and I'm expecting you to pick up those sort of nuances. If you go to the right here, you can see that there's a slight curve to the right, and that tends to let you think that the residue curves are moving in this direction towards the water. Yes, Shafilui.
So is that second blue line you drew on the right hand, the 1000 kPa one, also an azeotrope between the water and the benzene?
It's a distillation boundary, yeah. So the way I'm interpreting this thing is that there is, because of this very slight movement to the right here, that there is a distillation boundary.
So the slight movement,
that
if
means
you zoom in further, sorry, if you zoom in a bit further, you see that slight movement to the right is the lines for the constant composition. There's a slight shading on the lines of on the distillation boundary, well, on the residue curves, and the 3 lines around that blue point have different shadings. And if you look on the axis, you'll see they all go to the right, towards water.
I'm going to zoom in on the original tut. So you're talking about the different colors of those residue curves.
They shaded slightly differently. So if you take a look at the residue curves.
Yeah, the residue curves, but on the left, on the 101, definitely they're all going to the right.
Yes.
Are you suggesting that here at 0.1
they're also going to the right? Yes, sir.
You reckon so? Okay. I'm on the actual PDF. Let me just use Control to zoom in.
That slight movement to the
left
is the line of the constant composition.
The shading. Right. I'm just getting back to this thing. The shading over here between 0.1 and 0.2 on the axis.
Yes, sir.
That illustrates that this thing has actually turned to the right. I agree with you. I agree with you. So there is no azeotrope over here. So this line shouldn't be there, but it makes no difference to the way that we do this problem, fortunately. Okay, good. Right, I was having fun trying to color in this yellow section, pencil, and I'll do some more shading. Okay, so that's all shaded in, and that is possible because, wait a minute, I must get my pointer again. This area is possible distillate because, for instance, we can take a point over here on this residue curve. We can take a line that goes through the feed, and then on the other side of the feed, we can touch that same residue curve. So if we took, I don't know where I started, if I started over there, we take that residue curve, it runs all along the axis right through to water. And therefore, this point on that residue curve can go through the feed and cross the same residue curve on the other side. So all these yellow shaded areas are possible distillate. Distillate because the direction of the arrows are moving away from that point and moving towards water as the heaviest, least volatile component. On this side, on the bottom side, it's more difficult. So let me get my line. My line tool, go through the feed until I reach the axis. Now, if we want to color in the possible bottoms, we would need to color in between the residue curve and the straight line that goes beyond the feed. But it doesn't stop there because it'll go all along the axis. So I'm going back to my line tool, and I'm going to, it carries on from there right through to the bottom there where there's water. So all of this area here represents possible bottoms product. Okay, so that's normally 4 marks. I give a mark for each of the boundaries, so you show that that this red line is a boundary. You show that the black line is another boundary, the curve, and that boundary goes all the way to water. On this side, the black line is one of the boundaries, and this red line is the other boundary from there through to F. So as long as you've shaded in between those two boundaries, 4 marks. 4 easy marks. Okay. Right, now we can start looking at how we're going to do a process flow diagram from this. And there the question has actually told us that from the first distillation column, also at 101 kPa, we must make pure water. So we know that one end of this mass balance line is here. All right, just to summarize, so that one you've just posted, yes. Yakalui, to summarize, a part of the way to get the azeotropes is to look for the shading of the lines. A more reliable
way. The summary for the question above. It's not a specific question for now.
Okay. Yeah, and this is something that everybody can download and look through carefully. Yeah. If it changes direction, then there's an azeotrope. Yep. Because then it makes it a saddle point. Okay. Right. So going on to this thing, we've got a feed there, and I suggest that at 101 kPa, the first distillation column should make water. And then, of course, you would make this binary mixture of benzene. Is it benzene? That we got benzene. We've got a binary mixture of benzene and ethanol over here, and it's 72% benzene for that distillation column. Okay, now I'm going to scroll down, and let's hope that all my lines scroll. Oh, yes, they're scrolling with the document. So here we've got the feed. We are making, why did I write an F there? That should be, right, let me get my text tool and write that we are making water down here. Text tool, and we're making water. Okay, so we've got a feed, we're making pure water as the question suggests. This is 101 101 kPa, and up at the top we've got, it's a pity we're writing B, A, B, C. That's water. This would be A. Yeah, I wrote W. This should have been an A, which represents water. B represents that 72% benzene. Write it that way. And now we must see what we must do next. And now I'm going back up to the residue curves. And now we've got something that lies over here. Now what do we do with that? And remembering, we want to get into this distillation zone in order to make ethanol. If we distill this at 101, we're going to make that same, pointer, right, thank you. We're going to make that same azeotrope. If we distill this stuff, the 72% benzene, we're going to make that stuff, and we're going to make pure benzene. So wouldn't it be better to use that 72% stream at 1000 kPa We'll still be able to make pure benzene, but we're going to make the other stream is going to be 32% benzene. In other words, it'll be mainly ethanol. And so this is going to be a much better option because that point, 32% benzene, lies in that distillation region we want to get into. Okay. So let's have a look down again. I'm going to scroll down again. And what we're suggesting is this is going to be 1000 kPa. And this is C is pure benzene. And this W, we should actually be calling it A, which is water. Okay. So now D is that 32% benzene. Oh, spelling. Ay, ay, ay. Okay, let's go up again. So now we've got 32% benzene, and now we can reduce the pressure again. So this is pressure swing distillation that we're doing. And once we've reduced the pressure, we can again make that that azeotrope and pure ethanol. So let's have a look at that on our process flow diagram. There we go. I'm going to get the text tool. I've got the text tool. 101 kPa. And G is pure ethanol. Because the arrows of the residue curves are going towards the ethanol, and E is the azeotrope, benzene and ethanol. Next. Right, let's go back up to our diagram. So now, what do we do with this azeotrope? So that should clearly be recycled. And you can mix it with the feed and land up with a feed that is slightly upwards from where it lies at the moment. Yeah, Yakului.
Pointers up.
Sorry, say that again.
The pointer.
Pointer. For some reason, my normal pointer has changed to a hand, so I keep forgetting that I need to change to a pointer. Okay, so the last distillation column that we put in is 101 kPa. It makes pure ethanol, and it makes this azeotrope. And what do we do with that azeotrope there? So by now, the mole flow rate of this azeotrope is quite small. And if we mix it with the feed, we will move this feed composition up a little bit along this line, which would still be okay. Everything would work just fine. But the azeotrope is a binary azeotrope. It's only got ethanol and it's only got benzene in. So it makes sense that we would rather mix it with this 72% benzene. And therefore, once we mix it, it's going to probably lie over here, quite close to the 72% benzene. It will, once it's mixed, it might be a 69% benzene mixture, benzene and ethanol mixture. So let's go back to that process flow diagram. Here's the azeotrope, and where do we mix it? Do we take it back down to the feed here? Or do we take it down to that point where there's 72% benzene? And clearly this is going to be a better, well, not clearly, but this is probably going to be a better option to go down this way. What you have to do at this stage is recognize that oops, I must go back to the pointer. Yes, recognize that this stream is a binary stream. And when you take it down, there must be two places where those, because it's binary, it's got benzene and it's got ethanol in it. There must be two places where those two components can come out. So if instead of recycling it down there, we recycled it down here. I'm going to just draw a different colored line. A gray line. And we go from there to there. If we recycled it in that direction, I'm going to draw a boundary. Okay, there's nothing going out here. This line doesn't exist. If the recycle went down here, you'd have stuff coming in at this point, and there's stuff coming out there which is pure ethanol. So this stream coming in contains both benzene and ethanol, and there's no place for the benzene to go out. So this mass balance would never work if you do a recycle over there, because you've got both benzene and ethanol coming in there, and you've only got one place where the ethanol can come out. I actually drew this envelope at the wrong place. I just wanted to redraw it. Ooh, what's going on here? I just want to redraw it. To show that arrow going out. There we go. So if you've got two components coming into an envelope, you need to have two exits going out of the thing. Just going to go back to that and delete it. I want to delete this one. So let's put in the envelope for this recycle. We've got I have got the right thing, yes. Got that. We've got benzene coming out, we've got ethanol coming out. So there we've got only two components at the top of this distillation column, and we make sure that we have got two places where those two components can come out. Then you know you've got your recycle at the correct place. Okay, any questions on that? Let's take a pause at this stage. In a test or exam, how are we going to draw lines or shade in the diagrams? That's where I'm going to have to be creative. I don't know the answer to that one yet. It may be that I draw all the possible flow diagrams and and that you would have to choose which of those flow diagrams is viable. That's not going to violate the distillation boundaries. That'll be one way of doing it, because then you would need to understand how the tie lines work and what are possible areas of distillation and so forth. But that's something that I'm going to have to sort out. It's really going to be difficult. Yeah. Yeah, use paint. All right. Yeah, that's pretty much it. That is the way. Let's go back to this diagram again. I'm just going to remove the envelope. And this is the answer to that problem. And again, once you've drawn this flow diagram, you must make sure there feed has got right pointer. The feed is a ternary mixture, so there must be 3 places where each of those 3 components can come out. So here you go, water comes out there, benzene comes out there, ethanol comes out there, so there is a place for everything to come out, and therefore the mass balance is possible. So the number of kilomoles per hour going in here of each of these components will equal the number of kilomoles per hour of water coming out there. Now, so the number of kilomoles per hour of benzene coming in there is going to equal the amount of kilomoles per hour of benzene coming out at sea. Number of kilomoles per hour ethanol coming in there is going to equal the number of kilomoles per hour of ethanol going out there. And that's it. So just take the time in your tests and exams to check that you have got those 3 outlets. And that's especially relevant where you choose where your recycles will go. And I get this mistake happening quite often, of people putting in the recycle too early. And this is a good answer where it goes in at B, but it would not be an incorrect answer. The flow diagram would still work if you took it down and mixed it with the feed. Okay, so that's it. That's the touch. I hope you all got it before I explained it to you. Good. I've got a happy face at least one. Good. Okay. You guys seem to understand it then. Oh, that's great to hear. All right, guys. TPB takes your time. Yeah, I've heard I've heard people are struggling on that one. Okay, well, then I better not take up your time anymore. Thanks for listening. Let me stop the recording and leave the session.